All right. So as far as this week's activity, I have on my schedule that you really at this stage should be through chapters 4 and chapter 5. So if you're playing at home, which you should be, know that that's about where you should be in the system. If you're ahead, great. If you're not there, then try and catch up because the rest of it starts coming at you fast and furious, and you're going to want to make sure that you don't get behind when we get into the chapter 7, chapter 8, chapter 5 to a lesser extent. Chapter 4 is basic electricity. Now, a lot of you guys may have had some electrical training or background. I always say that if you can wire an outlet, you can probably install solar. It's not that difficult, but of course, electricity in and of itself is something that you've got to be cautious about. You know, it's something that assume it's always trying to kill you. You know, that's just always a good assumption. I'm going to flip through the chapter here and just see if anybody had a question. There's a couple of the equations that you're going to need to know for the exam. The first one comes in chapter 4. It's watts equals amps times volts. It's the basic power equation. It's fairly straightforward, but it really is that watts, which is the amount of power, is volts, which is the difference in potential. You can think about the water analogy where volts is the pressure on the line and amps is the size of the pipe. And in combination, the water flow is the watts. So that's the analogy that comes through usually with electrical. So that's a pretty straightforward equation to understand. Watts equals amps times volts. Then there's the difference, and this confuses people sometimes, the difference between watts, watt hours, and watts per hour. Watts is a measurement of power. Watt hours is a measurement of energy. Now we buy energy from the electric company in units of watt hours. Now we buy them in 1,000s, bundles of 1,000, which is a kilowatt hour, but it's watt hours. We don't buy watts. Watts is an instantaneous measurement of power. We buy energy. So, and watts per hour, you know, that's different. That's a rate of consumption. The fact that everything is watts, you know, can confuse things a bit. The other issue, of course, with the transmission grid, it really is broken into 3 main areas. There's the generation end. And if you think about a traditional utility, that's usually been like a coal power plant. And it just generates power at a centralized source. Most power plants are glorified tea kettles. You know, all they're doing is boiling water and using the steam to run a turbine. So nothing fancy about that, whether it's a gas power plant, a coal power plant, or a nuclear power plant. That's pretty much all that they're doing. Of course, hydro, a little bit different. It's using the power of the water to spin the turbine. Wind, using the wind to turn the turbine. And then, of course, solar is a bit different in that it's a electron exchange process. And did anybody get confused a bit between the difference between single phase and 3-phase electricity? Let you guys feel free to speak up.
I thought it was interesting, but it's still hard to wrap your head around.
Well, most of the residential sites are going to be single phase. One of the big advantages of 3-phase, if you think about a single sine wave where you've got, you know, a curved sine wave that goes like positive 240, negative 240, positive 240, negative, that happens 60 times every second. So 60 times every second, the voltage is at 0. So you end up getting a bit of a vibration in that. And that's why a lot of these heavy motors and the like 3-phase, because these waveforms overlap. So the voltage is never at 0. So you get a much more constant much more universal power source through three-phase. We don't get much into three-phase. What I really want you to be aware of, oh, let's see, am I not sharing my video here?
No, you're a little dark.
Yeah, I'm just saying, there we go. That's something. Oh, I see what's going on there. All right, there we are. I just noticed I've got two screens up and I'm seeing myself on one screen, but then over there, I'm not seeing, I'm just in the dark. Okay, so yeah, the main thing, the main takeaway that you need for solar is when you start looking at an inverter, for example, and it says it's 208, 120, you know that that's a three-phase inverter. If it says 480, 277, you know it's a three-phase inverter. If it says 240, 120, well, it's probably single phase, but it might be a three-phase. There's a weird 240, 120 three-phase. But and of course, if it says 250 volts, you're probably looking at a British website and you're about to buy something that was for the England marketplace and not for America. So we want you to make sure you're buying the right equipment for the right job. And when you get into some of the larger systems, oftentimes you're going to be buying, for example, a 480 277 inverter, and then it may step down at a transformer on site. So it comes in from the utility or from the array at 480 and then steps down to like a 208 120 system. This is what the system is there at Eastern West Virginia Community College. That building receives energy from the utility at 480 277. And then if you go out there by the trash bins and all of that, there's a little building there where the connection is and the meter is and all of that. And there's a transformer there. So you can just look at it. And at that location, it's being stepped down from 480 down to 208 120. The other big thing to understand is, of course, the difference between series and parallel. That's something we spend a lot of time on in the chapter. So make sure you really understand that, because if you don't, you're going to be in trouble, all the way down the road. There's kind of no substitute for just knowing it. When you hook up panels in series, voltage increases, but amps remain the same. If you hook them up in parallel, amps increase, but voltage remains the same. I've got a little trick you can use if you want to try and remember that if you're having trouble, is there's no A in series. If you think amps, A, there's no A in series, so it's volts, where there's an A in parallel, so it's amps. That's something you can use. But and then the second equation that you need to understand is the Ohm's law. Ohm's law is volts equals amps times resistance. That's just VER, V equals I times R. Similar to the power equation, which is watts equals amps times volts. If you know two of the things, you're going to be able to figure out the third. So Ohm's law is just saying there's a relationship between these three things. Brian?
So why would, I've worked on vehicles and that's 12 volt, and I know that coming into a house is 240 volt. So why would we increase something to 48 volt? Is that just so that you could use the smaller wire?
Yeah, that's the primary reason. Yeah, at 12 volt, if you were operating a home, and in the early days of solar, they were all 12 volt. But the wires ended up just getting huge if you had any kind of power, at all in the system. So they increased the voltage of the DC system as much as they could. But the NEC had the rule that you couldn't have batteries inside your home higher than 50 volts. So they capped it off at 48 volt, largely because the NEC had that limitation. So most of the homes ended up standardizing on 48 volt, so that all the systems pretty much, unless you're talking about really small systems. If you go to Harbor Freight, you're still dealing with 12 volt batteries, 12 volt systems. But if you're looking at a home size system, it's going to be 48. And now we're actually able to increase the size of the batteries with the new NEC rules if the end user customer can't touch the terminations, if it's something that's sort of self-contained, so that the average homeowner can't go in and hook anything to it or come in contact with any of the live parts. Then they've said, okay, now the batteries can increase to whatever the limitation of the building is. So in a residential, that would be up to 600 volts. In a commercial property, it'd be up to 1,000 volts. So you're now getting batteries, like the Tesla Powerwall or something like that, where the voltage is going to be significantly higher than 48. It might be 400 volts within that battery bank. And the reason for that is because it just saves them money in the production. They can use smaller wires. If you think about it, I've got a solar array coming in at 600 volts. I need to convert it down so that it's charging a 48 volt battery. And then that 48 volts feeds an inverter that then increases it to 240 volts. Well, that 48 volt is a significant step down. So if I could go 600 volts to 400 volts to 240 volt, it's just a cleaner, smoother transition. So that's kind of where we're moving to. But for the test, battery limitations in a building, 50 volts or 48 volts, whatever. I think it's 50 volts AC, 60 volts DC, but it's basically a nominal 48 volt system. So.
Gotcha.
All right. So resistance is measured with Ohm's law. And on page 84 of your book, there is a resistance table there that measures the resistance. And this is provided by the NEC. And what they've done is they've just gone out and taken 1,000-foot spools of cable and measured how much resistance there is in 1,000 feet of wire. So they're giving you the resistance based on per 1,000 feet. So that's why the voltage drop equation, which is the third equation you need to understand or to remember, is based on it reduces the voltage drop or the resistance based on 1,000 feet of cable. So I know I'm not explaining that very well, but let me see. I've got the whiteboard thing here. Everything's all piled up. Here's my pen. So I'm going to see if I can share this whiteboard here and I'll new whiteboard. Oh, yeah. So what the voltage drop equation is, voltage drop equals amps. Well, what are the amps? Typically, the amps are going to be IMP. That's the amps at the maximum power point. So that's the operating amps of your system. It's not the theoretical maximum. We're trying to know what it actually is functioning at. And then we're saying times resistance. Well, if we stopped right here, this is Ohm's law, right? Volts equals amps times resistance. But the resistance that we've been given is per 1,000 feet. So we need to multiply this times twice the distance divided by 1,000 feet. So why is it twice the distance? It's because the wire is a circuit. So it goes there and it goes back. So if I've got to run from say the combiner box up on the roof to a DC disconnect down here, and it's 250 feet, and the IMP of my system when I measure it is, let's just say 8.6 amps. So then I could calculate the voltage drop equals 8.6 amps times the resistance. Well, we would get the resistance off of the table on page 86. So let's say that we're using, or page 84. So if I'm using, for the heck of it, 12 gauge wire, stranded, So that's 1.98. So looking at that table, 12 gauge wire stranded is 1.98 ohms. Whoops, I'm getting off the. All right, how do I get rid of that? I'm getting teardrops up there. There we go. 1.98 ohms. But that's 1.98 ohms per 1,000 feet. We know it's 250, so it's going to be 500 feet, twice the distance, divided by 1,000 feet. So it's going to be 0.5. So down here, I'm going to jump down here. The voltage drop is 8.6 times 1.98 ohms times 0.5. All right. I'm seeing Ted's thing jumping around. I don't know who Ted is on that. Oh, Ted, you're there. I didn't know that we could collaborate on that. That's interesting. So if I take 8.6 times 1.98 times 0.5, and I'm getting 8.5, right? 8.514 amps, or sorry, volts. So doing this, I just discovered that for this run from this combiner box to the DC disconnect, given the wire size and the amperage, I'm going to lose 8.5 amps or 8.5 volts over that distance. Well, Brian, this gets you into that kind of thing of, all right, what if I'm working on a 12 volt system? Well, I just lost 2/3 or better of the power going from the array to the DC disconnect due to voltage drop. Well, that's significant. I've just lost 70% of all of my power. But if I go 48 volts, well, if the system is 48 volts, then it's 8.5 divided by 48. I've lost 18% of my power. Well, that's still bad. I mean, that's really bad, not as bad as 70%. So what can I do to reduce that voltage drop? Well, I can go with bigger wire. That's going to lower the resistance here. Give me a smaller number, which is going to give me smaller voltage. I can reduce the distance. That's going to give this number, make that smaller, but usually you design it based on what the realities of the situation are. Or I could increase the voltage of my system. Well, what if I increase this to 600 volts, coming from my array and then stepping down? Well, at that point, 8.5 volts out of 600 is only 1.5%. Well, now we're within the realm of acceptability. So this is one reason why we want to increase the voltage of our system as much as possible, is because we want to, you can see I'm using. So how do we deal with that? This is not one I'm used to doing. I wanted to get a new page here. Whoops, I'll go back in. So those are some of the issues with voltage drop. The higher the voltage, and typically then this is jumping a little bit ahead, but if we've got a solar array here, the first step is going to be a junction box or a combiner box, and then we're going to go down here to a DC disconnect. And then let's say that this is a standalone system. Now I've got a charge controller. And from the charge controller simply takes the power from the array and puts it in the battery. So I've got a battery. And from the battery, usually you're going to go to another DC disconnect of some sort. Then to the inverter. And from the inverter, we're going to go to our load distribution panel. All right, this is a fairly typical standalone system. So the array to some sort of combiner or junction box, DC disconnect, charge controller to the battery, from the battery to the inverter, and from the inverter to the load. then very often we have a generator of some sort, and it connects into the inverter. So that, and that's just there so that you don't have to design your battery bank for the worst case scenario. You're designing it for the normal operating situation, and you've got a generator to back it up. On let's say you get an extended snowstorm or extended period of time when it's not generating. So if we're coming in the olden days with one of these systems, I had to have a 48-volt array, a 48-volt charge controller, a 48-volt battery, and a 48-volt inverter. Okay, all of these things, and these are nominal voltages, but all of these things needed to be compatible. So then you would see that your voltage drop would be significantly impacted because I'm leaving here at nominal 48, maybe going a great long distance. But not too long ago, just a few years ago, maybe a half dozen years ago or so, somebody got the bright idea that we could incorporate a voltage to voltage converter within the charge controller. And their first step is they said, I can come in at 150 volts and I can leave at 48. Then very quickly, they increased that to 250 volts. And today, most of them are going to be, say, 600 volts. So I can come in from the array at 600 and then leave at 48. And the reason that helps is you can use a lot smaller wire for the portion of the system where there is a lot of wire. And so I can create an array here that's up to 600 volts and then step down in the charge controller and go to a 48-volt battery and a 48-volt inverter. So that saves a significant amount of money on our system. And these charge controllers, unfortunately, have been named MPPT charge controllers, which is not a good name for them because the MPPT, the maximum power point tracking, has to do with the array, keeping it in the sweet spot on the IV curve. And all charge controllers have MPPT built into them, but they've decided everybody likes the term MPPT. So they did. So that's what they call them. But it really is just a DC to DC voltage converter charge controller. And the technical term there would be a buck boost charge controller. It can increase or decrease the voltage. Have I confused anybody with any of this? Hopefully this is a bit of review. If it's not, you're lagging behind. So that all has to do with wire size. That's the issue there. Okay, grab this. I know I'm kind of rambling through this because none of you guys are, well, Brian is speaking up occasionally. So he gets a gold star for today. The rest of you are probably, you're all like eating your lunch or I don't know, watching the Smurfs or something.
School was wasted on me. I should have done that now.
Yeah. Yep. Okay, so then bonding and grounding. We touch a little bit about bonding and grounding in this chapter. We'll get into it a little bit more, but it's funny, when I first started studying solar, bonding and grounding was this great, big, scary world. And everybody would say, oh, pay attention to bonding and grounding because it has to do with life and safety. So really all that it is any surface that can conduct electricity can become energized as you're working with the system. And usually it becomes energized because some piece of wire that wasn't supposed to be touching it is touching it. For example, if you've got a little piece of wire pinched between some solar panels and over time it wears through the insulation and now the metal contacts are touching the aluminum frame of the solar panel, that whole solar panel could become a live wire essentially. So any of the metal bits have to be connected together and then provided a pathway to ground. to take any stray electricity that might come in contact with those metal bits and give it a good low resistance pathway to ground. If there's a wire there that's drawing that power into the ground, when you touch it, you're providing a pathway to ground, but you're more resistive than the wire. So you may feel the tingle, you'll feel it, but it's not going to kill you. If there was no pathway to ground, you would provide that, and the electricity would flow through your body to the ground. So that's what bonding and grounding does. Just connects all the metal bits together. You stick something in the ground, and then you connect the system to it. And that thing
Jay?
that yeah.
Hi, this is Ted.
Yeah.
On the sort of the scenario you just mentioned, if the wires were frayed and were connected to the aluminum frame on the rack and then a metal pole or a mast, isn't that it's unintentional, but that's kind of the grounding you don't like, but it is grounded?
Well, that would be referred to as a ground fault. So there is now power running to the grounding system. The grounding system assumes there's no power on it. It's just there to receive power if something goes wrong. So if the wire gets frayed, yes, now it's a ground fault. And your system is designed to shut down when it senses there's a ground fault. So in the inverter, there needs to be a ground fault detection device that says, hey, power is on the grounding system, the equipment grounding system somewhere. We better shut down because this is a bad situation. And often you'll see the circuits pop, the breakers pop or something like that. And so it does shut down. But what you're referring to there is a ground fault, but the grounding system exists there all the time. Does that make sense?
It does. Yeah.
Okay. Yeah, I'll give you an interesting example that happened in my life. We have stainless steel cabinets in our kitchen at our farm. So the entire cabinets are made of metal. And my wife came to me one time and said, there's something wrong with the microwave because when I touch it, it gives me a shock. And I said, well, is it like a static electricity? And she goes, no, it's like, it hurts. It's like a real shock. And so I went up to it and I'm like touching with the back of my hand because you don't want to grab onto something. And I didn't get any kind of nothing, it didn't do anything for me. So then I said, well, she must have just, I don't know what caused it, but she came back and said it did it again. So I went and I looked at it and at some point I got shocked and I thought, wow, that's like live electricity. Well, what ended up happening, it wasn't the microwave. It turned out it was one of these electric tea kettle things. And over the years, that thing being shifted around on the countertop had worn the wires in the bottom of it bare, and the bare wire was touching the metal countertop. So the entire counter in our kitchen was energized. It was operating at 200 or 120 volts. Had there been a small child, in the house or something coming up and touching that, it could have been catastrophic. We just felt the shock. Now, it didn't shock me initially because I was wearing tennis shoes. So I was insulated from it. But you wouldn't normally think that you need to then bond your kitchen counter and run a wire to a rod and stick it into the ground. That's not something that normally would come in contact with electricity. But your electrical system, your solar system, yeah, it's in contact with the electricity. And if there's no pathway to ground, it's just sitting there waiting for somebody to touch it. And then your body provides that pathway to the ground. And that's how people die. And I saw a really cute picture one time in a magazine where it said, why is bonding and grounding important? That was like the headline. And underneath was a picture of President Obama at that time visiting a solar array, and he's touching the solar panels. And it says, because you never know who is going to touch the metal parts of your system, and could you imagine somebody electrocuting the president because they did a crappy job of bonding and grounding their system? So Anyway, that's all bonding and grounding does. There was a note about ampacity. I think we'll jump into that since you had a question about ampacity. The note popped up.
Yes,
Ted?
that was me.
Uh-huh.
I is Ted, and I went through the ampacity lab, and I had a lot of questions about the. I guess it was the math that you used. For instance, I'll jump right into when you go to multiple wires in one conduit, let's say
Mhm.
4 to 6 wires. I'm just recalling, it was 80%. It was, I guess is it a reduction of 80% of the current that goes through there, or you have to account for that?
No, it will only carry, or it will only have the ability to carry 80%
Right.
of what it
Okay.
otherwise would have been rated for.
And so when it got to the ampacity lab, you took 80% and divided it into it to get a greater number of amperage. And I'm
Yeah.
puzzling over why you did that.
Yeah.
Instead of just multiplying it,
Yeah, if you multiplied it, what we were
you get a
trying to do
reduction.
is kind of work backwards. Because you're saying, okay, based on this, what size wire do I need?
Right.
As opposed to saying, this is the wire I'm starting with, how much will it handle? So if I had taken, let's say, I need a wire that will carry 30 amps, for instance, but it's going to be in a conduit filled with other ones. Well, if I took 30 amps times 0.8, I end up with a smaller number. And then I would get a smaller wire. Well, that doesn't make any sense. I need a bigger wire because the capacity has been diminished. So it's because we're kind of working backwards. Let me
Okay.
yeah, let me try and do that on the whiteboard here. Maybe that'll make more sense. Okie doke. Yeah, this is the whiteboard I was looking for before. Okay, so if I just say, let's say we're starting with an output of 30 amps, and I've decided that it's diminished by that it's going into a conduit, and that conduit fill is going to be 80 amps or 80%. If I did 30 times 80%, that's going to be 0.8, and 30 times 0.8,
24.
24. I should just know that. That's terrible. So that's going to equal 24 amps. Well, if I looked up in the book, what size wire do I need to carry 24 amps? I would end up with 12 gauge
Smaller
wire?
wire. Yeah, smaller wire.
Too small. So yeah, so what I end up doing, because I'm really trying to determine the wire size, is I'd say 30 amps divided by 0.8. And now that's going to be 37.5 amps. And now I need to look up on the table. And which page is that table? Is it like 100 and
106.
106? Yeah. And so if I look at 37.8, my guess is it's going to be more like 8 gauge wire. We run into this same issue, or 104. There we are.
104.
106 is where the table for conduit fill is. Yeah.
Okay.
So if we look at this, then yeah, we're going to need 8 gauge wire because it's 40 amps. So logically, it makes sense that if the capacity of the wire to carry amps is reduced, I should need a bigger wire.
Yeah. Okay.
And so if you you run into this a lot, let's say if we're derating our system, let's say we decide, and this is in a future chapter, that our system that we've configured will generate 3,500 watts. But it's only 90% efficient. So if I derate this and I say, okay, times 0.9, then 3,500 times 0.9 is going to get me 3,150. All right. So in this case, we would do that to say this is what that system is outputting. If this is D rate, which is the inefficiency of the system, I would do it this way. But if I say I need it to generate 3,500 watts, what size system do I need in order to do that? Well, if I multiplied it times this, you would say, oh, I need a 3,150 array to generate 3,500 watts because it's not efficient. Well, that doesn't make any sense. So then I would divide by 0.9. And now I need a 3888, you know. So a 388889 watt array because it's only 90% efficient.
Okay.
So this is something to bear in mind when you're doing these things, you know. I just think, do I need a bigger number when I'm done, or do I need a smaller number?
Right.
You know, and if you get a smaller number, you did it backwards.
Okay, and related ampacity, and also in that same table, or that same quiz, and I could not find it in the text. I could have just missed it, and I could not get to the NEC section in one of the
Yeah.
earlier chapters. I just couldn't get it. But you introduced NEC safety factor of 1.25 and a solar variability factor of 1.25, which were multiplied times whatever the amperage was for any of the wires. And so I just had to go through the quiz a couple times until I figured out what math you were working on there. I had not seen that safety factor on any of the tables or a footnote or anything.
Yeah, it's not in the table. But it's in the textbook for sure. And it's in the code. So one thing to bear
Figured it
in
was in the
mind.
code. The code was what I could not access. I figured it was in the code,
Yeah.
but I did
And-
not see
and-
it in the text.
Yeah, I can't, I know that's an issue at the moment. There is a lab in there, and they used to let you just sign up and get access to the code
We
online.
figured that out.
Yeah, they seem to have cut us off on that. Yeah, Brian?
So actually Mason figured that out. If you go right out of your text, it's the older version, but since we have a 2023, you just have to Google the 2023 version of that NEC regulations, and you can still get in for free. You have to set up a login, but you can do it.
Oh, okay. All right. Well, that's good to know. So I can, when I update the textbook and the online version, which I'm working on right now, I'll make that live. But yeah, okay. So you can jump out of it and just go in and find it. Yeah, yeah.
But you found those ratings, those 1.25, the solar variability didn't seem to be a NEC rating. It might be, maybe it is. The NEC safety factor was 1.25, and I just have to accept it because I didn't see any other reference to it.
Yeah, it's definitely in there, but it's very well hidden. The solar variability one. Because I, in fact, just in December of last year did some research on that and ended up finding it, but it's like in a footnote. It's in chapter 6 or in article 690. Somewhere in that section is the solar variability. And what they're dealing with, or what he's bringing up, is, let's say that our wire leaving the array, we've got one string, and that one string, the ISC of that panel, and because there's only one string, whatever the amps are of one panel is the amps for the whole string. So let's just make an assumption this is 9.1 amps. Well, with all wire, when we're sizing the wire, we've got to size it based on, we've got to put a safety margin in. And the NEC requires that you multiply that times 1.25. And that's for every kind of wire in every situation. Electricians just get used to that, that you've got to have that safety margin because they don't want you pushing right up to the limitations of the wire. So 9.1 times 1.25 is going to be 11.375. But then, because solar is variable, and the reason we're saying that is this 9.1 was based on 1,000 watts per square meter at STC. And if you remember, at the outside edge of the atmosphere, it can be as much as like 1360 or so watts per square meter. That's the solar constant. And I've made measurements with a meter on like a clear, nice winter's day. And I've gotten measurements as much as, say, 1,200 watts per square meter on the ground. So everything's based on 1,000 watts per square meter, but that panel might be subjected to higher. It may be getting 12. So they say because of the variability, let's just put another 1.25 safety factor here. And so now we're taking this times 1.25, and now we're up to 14.21. Now, this only applies until you hit the first electronic device that's going to be mitigating that variability. So if this were a, let's say a standalone system, one string, all right, we need wire 14.21 amps here from the panel to the combiner box. Well, normally that's going to be the wire that comes with the panel. It's going to be hooked up to that panel and you're just going to be running strings into the combiner box. Well, in today's marketplace, that's always 12 gauge wire, pretty much always. Well, if you look at 12 gauge wire, it has an ampacity rating of like 25 amps. So we're fine. We're fine for that 12 gauge wire. Okay. So what would happen if I had like 4 strings coming in and being combined? Well, each of these strings would have an ampacity rating of 14.21 amps. But in the combiner box, they're being combined into just one pair of wires. Well, I've already derated them up here. So now I just simply multiply that times 4. And now that's going to be 56.875. So what size wire do I need here? Well, I could look at the table and it would say 6 gauge wire in column 1 is 55. I need 56. So I'd have to go to 4 gauge wire. If everybody's looking at the book, do you understand? Now,
Yeah.
Notice if I had gone with a heavy or with a higher temperature rated wire, if you look in column for 6 gauge wire, if I go with a 90 degrees Celsius rated wire, it can handle up to 75 amps. So why wouldn't I just do that? Why wouldn't I go with a higher rated wire? Well, the issue there is I certainly could. I could do that and it would be all right. But remember that this string here, this piece of wire, is not only the wire, but it's the connection point here and it's the connection point down here. So there are terminations there that I have to bring into account. If I have already bought these pieces of equipment and I look at the DC disconnect spec sheet and it says the terminations are rated to 90 degrees Celsius, and if this combiner box says that the terminations are rated to 90 degrees Celsius, then I can use wire from the 90 degrees Celsius column. But if I haven't bought those products yet, if I'm just designing this system and I don't know what's what yet, or if I think I might switch out the products in the future, which happens more regularly than you would think, the better design thing is just always pull your amps from the first column. That's your worst case scenario. So if you don't know what the terminations are rated for, or you think that the equipment might change in the future, just use column number 1 when getting amp ratings for wire. You're never going to be in trouble putting bigger wire in. You only get in trouble if you put in too small a wire. It may cost you a little bit more, and wire is getting increasingly expensive. So a lot of people are trying to shave every bit. So, but you've got to know those terminations if you're going to pick the higher temperature wire. So in this case, I'd have to run, well, let's say I decide to go with 6-gauge wire right on the edge, and it's got a rating at the temperature that I've selected. It's got a rating of 65 amps. Well, what if this is 300 feet from here to here? Well, then I've got to calculate voltage drop. So voltage drop equals, well, what would be my voltage here? Well, amps are already, now in this case, we don't want this number, 56.185. That's the derated amperage. We want to know what are the actual amps. We don't want the 1.25 and 1.25. So in this case, I would look at the IMP, and let's say that the IMP for this panel is 8.6 amps. Well, then it would just be 8.6 times 4, because they're being combined in here. And 8.6 times 4,
50.4,
34.4.
34.4.
34.4 amps. So it's the IMP, which is 34.4 amps, times resistance. Well, I look up in the table, and the resistance on this wire, we decided we're going with 6-gauge, is 6-gauge is 0.491. 0.491 ohms times, well, I said it's 300 feet. 300 feet times 2 divided by 1,000 is going to give me 0.6, right? 600 feet divided by 1,000. So then I take the numbers here, 34.4 times 0.491 times 0.6. So I'm now going to lose 10.13 volts. Is that acceptable? Well, might not be. What if this is a 48 nominal volt system? So this is 48 volts up here. Well, I'm losing 10.13 over 48. So I've just lost 21%. And we want to keep our voltage drop between, we want it to be around 2%, ideally, for the whole system. So that's just not going to work. What would happen if I increased the voltage of this? Well, if I increased it to 480 volts, it would be 2.1%. So, increase the voltage 10 times. Or let's say that I didn't want to increase the voltage. I don't have an MPPT charge controller. I need to get this thing down somewhere below 5%. Well, what size wire am I going to need? Well, at this point, what if I went with 2-gauge wire? So we look at the resistance table there for 2-gauge. I can't remember what page that's on now.
84.
84. So that's why I didn't find it. I'm already past it. All right. So if I say 2-gauge wire, well, now that's 0.194. 0.194. Everything else stays the same. 34.4 times 0.194 times 0.6. So it's still at 4%. Or sorry, 4 volts. 4 volts. So if it's a 48 volt system, I'm still somewhere around 8%, 9%, somewhere in there.
Mhm.
So really I'd probably have to go with 4-aught wire. So that's 0.0608. So I'd go 34.4 times 0.0608 times 0.6, 1.25. And 1.25 volts. Divided by 48 is still 2.5%. So if I went with 4-gauge wire, I'd be dealing with still a 2.5% voltage drop. Well, how much does 4-aught wire cost? Like $3 a foot times 2, because you got 2 conductors. So $3, $900, $1,800 just for the wire to go from here to here. That's pretty pricey. Be a lot nicer if I could go straight to a charge controller that allowed me to come in at 600 volts and leave at 48 volts. This charge controller here cost me $175. So if I'm up here at 600 volts, then, you know, my amperage goes way down. Because how many strings do I need? Well, in this case, I probably only need 1 string. The 1 string is going to be only about 14 with all the adjustments, 14 amps, 14.21 amps. So now we got a 14.21 amp system, and you can see we can probably get by with 10-gauge wire, you know, for sure. Now, I never want anybody to use less than 10-gauge wire if you can avoid it, because even if you can get by with 12-gauge or 14, don't use it. You know, you're going to get yourself into trouble. So use 10-gauge as a minimum for your systems. Okay, I know that was a lot of stuff in there, but hopefully you'll that will give you a sense of why we're trying to learn all this stuff. We're really trying to learn it just so we understand how to wire the system safely. So go through some of these practice problems and make sure they, you know, make sure you begin to understand how sizing the wire impacts, you know, why we have the safety margins, how voltage drop affects it. I'll tell you the rule of thumb that electricians tend to use is they say if the run is more than 100 feet, get one size wire larger than you think you need. So if I'm running 20 amps over it, but it's more than 100 feet, they'll probably just say put in a 10-gauge wire, not a 12-gauge wire. That's kind of how they do it. It's it tends to work, but it's also not very elegant. So, and you wouldn't pass the test if you tried to do it that way. You've got to actually do the work, you know? So, anyway, so that's the concept there. All right. I know we're coming up on the hour. Does anybody have any quick question before we adjourn for today? Well, good. You finished your lunch? Okay, doke. All right. Well, we'll call it a day and we'll meet again next Tuesday. All right. Okay. Take care, everybody.
Alrighty.
Thank you.